confused myself. I think this is where we stopped last time. If y'all have more than this done, let me know. But I'm pretty sure that's where we stopped. But anyway, so I'm gonna start here because I assume this is where we stopped, but something happened that confused me and now I'm not sure. So remember, we're essentially finding area between two functions. Now we kind of skipped over this formal piece, so in case you are filling out those notes, I'm going to go over that really quick. But essentially, it essentially covers in less generality what this covers up here. So say we have f and g continuous functions, and g of x is less than f of x on some interval. So essentially that means that the g of x is going to be the bottom function. We were mentioning bottom and top functions before. Then the area between the two graphs is going to be equal to the integral from a to b of f of x minus g of x, which is essentially what we had already said the other day. We were doing top minus bottom, and that's exactly what this is saying, just in more formal terms. So let me remind us of what we were doing. Let me kind of go over this example really quickly to review what we were doing, and then we'll do this next one down here. So we want to find the total area, excuse me, for x cubed. And so remember, the point is that sometimes if you have area below the x-axis, it counts as negative area. And if you have area above the x-axis, it kind of counts positively. So if we have this situation with x cubed going from -1 to 1, we end up essentially having the same amount of area in each piece, so they end up canceling each other out. And so essentially with these, we're essentially asking not the general integral, but how much stuff is there. So we kind of have 3 steps. We need to find where the two functions intersect. We need to split up the interval if necessary, and then we need to find which function is on top of the other. So that's what we did for this one. We set x cubed equals 0, found it was equal to 0 at 0. So since we were going from -1 to 1, we had to split it at 0. This piece over here was the top minus bottom piece, sorry, top versus bottom piece. And remember, there's 2 ways to do that, either algebraically or by the graph. The graph is right over here. But then algebraically, remember, that's essentially when you pick a test point between the 2 points of the interval, plug it into both functions, see which y value is larger, and then you write out your integrals in terms of top minus bottom. The one last thing I was going to write on this one, and I think I ran out of time last time, was I was going to write the antiderivatives. So remember, with these, when it comes to doing these final answers, you can punch these into your calculator. But if you don't have a calculator that can do them, then of course you'll have to do the antiderivative, plug in the top bound minus plug in the bottom bound piece. So I'll usually write down the antiderivatives, and if you want to see any more steps than that, let me know. But essentially, if you type both of those into your calculator or you do them by hand, you should get 1/4 in each piece, so then the total amount together is 1/4. So that was a super quick review of what we're doing here. So let's go down to this next one that we haven't done yet. So we have this here. So the first thing we want to do, so we want to find the total area. So remember that essentially, since there's no official second equation stated, remember when it says total area or area between a function and the x-axis, then your other function is y equals 0. So we essentially need to set these two equal to each other to find where they intersect. So we have x cubed minus 7x squared plus 11x equals 0. Since all of those terms on the left have a x in it, we can pull it out. And then the nice thing is that this is goodness. Oh wait, no, this isn't factorable. I'm sorry. This is a not nice one. So here we can't actually factor this. So I'm getting ahead of myself a little bit. Since we have the two things that are multiplied together to be 0, one of the two must be 0. So we get x equals 0, but then when we want to set that quadratic equal to 0, that's not factorable because there's not two numbers multiply to 11 but add to -7. So we're going to have to use the quadratic formula. So remember, quadratic formula, -b plus or minus the square root of b squared minus 4ac all over 2a. So that would give us, if we take negative b, since b is already negative 7, that'll turn into a positive 7, plus or minus the square root b squared minus 4 times a times c all over 2 times a. If anyone wants to see oh my goodness, any more of the algebra on that, please let me know. But this will give you 4.618 and 2.382 approximately. If you want to see the algebra on it, just let me know. But those are the two numbers you'll get from it. So remember, this does give two answers because of the plus minus in the middle. You have to calculate one of them with the plus and one of them with the minus. Now notice the interval we're going over is 0 to 4. So that 4.618 is not in the interval we're working over, so we don't care about it. So we only care about the 2.382 and the x equals 0 that we got from the other piece. Well, we almost don't care about the x equals 0 because that's already an endpoint, but it technically does fall in our interval. So now that we have those points that fall in the interval, we're going to have to split it up at those points. So again, we're not going to split it up at 0 because it already starts there. But we're going to need to split it up at this 2.382. So it doesn't turn out very pretty, but we got to do it. Let me try to save myself. That's not going to be enough space. Let me try to squeeze this over here a little bit. So we don't use it because we're given in the original problem an interval from 0 to 4, and 4.618 is larger than 4, so it's not in the interval we're working over. If this was an interval from 0 to 6 or 0 to 5, then we would. But since it's outside of the interval we're given, we don't use it. So I'm going to do algebraically and by graph for the top bottom pieces. I'll always do both. Remember, it's one or the other when you're actually doing it, but I'll do it both ways in case people prefer one over the other. So you have to do, if you're doing it algebraically, you pick a point in each one of those intervals. So I'm going to choose x equals 1 for the first one and x equals 3 for the second. So we're going to want to plug it into both equations. So if you plug in anything to y equals 0, you just get 0. Because there's nowhere to plug anything in. And then if we plug it into the x cubed minus 7x squared plus 11x, so can I just write x cubed dot 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 over here because I'll run out of space otherwise. So if we plug them in there, what we're going to get if we plug in 1, so 1 minus 7 plus 11 is going to give us, where is it, 5. So which number is larger, 0 or 5? 5 is, so the x cubed function is going to be on top there. And then if we plug in 3, so essentially 3 cubed minus 7 squared plus 11 times 3 will give us negative 3. Which number is larger between y equals 0, sorry, 0 or 3? Sorry, 0 or negative 3. 0 is larger, so y equals 0 is going to be on top in the second interval. Let me remember to breathe and slow down every once in a while. If we were to do this graphically, our graph kind of looks like, not really to scale, but this is what it'll look like, where this is the 2.382 and this over here is the 4.618. So we're kind of going to stop like right here. So which function is on top of the other when we're comparing that that x cubed thing to the y-axis? Sorry, x-axis. The cubic will be on top in the first piece, which is exactly what the algebraic way got us. And then the x-axis will be on top, which again is what we already had. So we're ready to set up our two integrals. So we have one integral from 0 to 2.382, and then 1 from 2.382 to 4. So it's always top function minus bottom function. So our top function for the first interval is x cubed minus 7x squared, oh, I'm going to run out of space, minus 11x. And our bottom function is 0, and should always be a dx. I'm running out of space a little bit. Let me try to zoom in so I can write it down, and then I'll zoom back out in a second. This will just help me write it down and not look obnoxious. So let me rewrite that. So x cubed minus 7x squared, was it plus 11x? Minus 0. And then in the second piece, the y equals 0 on top was on top, so we'll have our top function minus our bottom function. Here we'll definitely want to put the bottom function in parentheses, because otherwise we will probably forget to distribute the negative, and we'll be wrong if we're doing this by hand, or even just punching it into a calculator. Okay, let me zoom back out. Now, of course, again, at this point for these area types of questions, you can just plug those into your calculator. If you do so, you should get 7.72 and then 5.05. Well, let me go ahead and write down the antiderivatives in case anyone's doing the antiderivative way. Let me move this a little bit. There we go. So the antiderivatives would be 1/4 x to the 4th minus 7/2, nope, 7/3 x cubed plus 11/2 x squared. I'm going to drop my plus c because I'm going to run out of space. And remember, when we do the bounds, the c's always cancel each other out. So because I'm about to run out of space, I'm just going to drop it. And then plus 7/3 x cubed minus 11/2 x squared at your bounds that I can't fit. It's going to run out of space a little bit there. If anyone wants to see any more work, I can move over to a different page for those antiderivatives. Otherwise, you'll get a final answer of 12.77. Questions, concerns on how any of that came into being? Yep, what's it? Oh, my sound is off. Okay, now go.
Okay, before you start any quizzes based on 3 or 4, it doesn't matter how you do it, intersect or when you graph.
I'm sorry, could you say that again?
Before you start working on something like example 3 and 4, it doesn't matter how you do it first, you intersect or when you graph stuff.
You always have to start with finding where they intersect. So that, the place where you get to choose, so here, let me. So intersect is one step. And then kind of this middle piece in here is kind of the part where you get to choose. You either can graph it, or you can find which one's on top algebraically by taking a test point and plugging it into both functions. So that's the part where you get to choose. The intersection one you always have to do. But then after you find where they intersect, you can choose whether or not to find which one's on top of the other by either graphing it or doing it algebraically.
Oh, okay.
Kira, do you want the calculator way or the full out way? Because I can do either. Okay, so calculator way. And if you want me, I can do like one of each maybe. I'll do one of each. How about I do one of the integrals calculator wise and the other integral full out wise. So, sorry. Okay, I'll get to that in a second. So say I wanted to do this in my calculator first. So say I wanted to do, let's do the second integral in our calculator, and the first integral I'll do by hand in a second. So, oh, you can't see what I'm looking at. Changed the screen and you can't even see it. Woohoo! Well, actually, let me come over here really quick. And that's not the class that we're in. We're in this one. And we'll do whoosh. And so let me make a picture. You can't see that. So we're going from, you can't see that either. Wow. Let's zoom in a bunch. There we go. So what are we doing? 2.382 x cubed minus 7x squared plus 11x minus 0. And then we're doing whoosh. 2.382 to 4 of 0 minus x cubed minus 7x squared plus 11x. So say I want to do that second one in my calculator. So if I want to do it in my calculator, oh, come. That's when you hit the math button and number 9. And then you just plug things in, unless you have an older calculator, and let me know and I can tell you how to do that too. But so when you have a lower bound of 2.382 and an upper bound, you use the up arrow key to get to the upper bound of 4. Scroll over. I know writing arrow in the front seems a little silly, but let's just go ahead and make it look exactly like what I have written down. Whenever you want to use an X, you have to use the variable button right next to the alpha key. If you use anything else, it could potentially mess up your answer. So we want x cubed minus 7x squared plus 11x parenthesis scroll over x and hit enter. Jordan, if you were trying to type this sucker into an older calculator, Lord help you. But here's how you would do it. You would still hit Math 9. I'm assuming you mean an older calculator that's still a TI-83. If you have something besides a TI-83, Jordan, let me know. I'll probably have to Google it, though. So you still hit Math 9, and then it'll come up with FN int, and then you'll have to fill in a bunch of stuff. Cool. So here's how you do it on one of those guys. The first thing you're going to type in is you're going to type in the integrand, the thing that you're trying to integrate. So you would type in 0 minus x caret 3 minus 7x caret 2 plus 11x parentheses. And you're still going to use that. I'm pretty sure that variable button is still in the right, and still in the same spot right by the alpha button. Whenever you want an x, you want to use that. And once you have all that typed in, you're going to do a comma, which should be right above the 7. The numbers, the buttons shouldn't have moved between newer ones. You're going to hit that variable button again. It's much more complicated on a calculator. A comma. And then you're going to put in your bounds. So the bottom bound, 2.382, comma, top bound, end parenthesis. And take a deep breath. And hope you typed everything in right. So that's how you'll do it in your calculator. You'll get 5.05. So obviously there's more to the decimal, but I'm rounding here. If you were to do this by hand, so let me do the first one a bit more by hand. You would have to find the antiderivative. So this would be a bunch of essentially anti-power rules. So add 1 to the power, divide by the new power. And don't be like me and keep dividing by the wrong power. And then remember, when we're doing these by hand, well, you still kind of use your calculator. You take the top bound, plug it in everywhere you see an X. I'm going to massively run out of space. And subtract, which I have to do down here because I ran out of space, what you get when you plug in the bottom bound. The C's are always going to end up canceling each other out. And if you were to punch all that into a calculator, because of course I don't expect you to do that in your brain, you should get 7.72. And then you add those two numbers together. Okay. Sydney, so once you have... Oh, okay. Which kind of ties into Anastasia's question. So let me go back to that. Algebraically finding which function is on top of the other. Well, actually, are there any questions about any of that I just wrote down? David, is your hand still up from before? You got a new question. I wasn't paying enough attention.
Or we gotta do it. My bad.
No, you're fine. I just wanted to make sure. Okay, so a couple people on the top versus bottom thing. Let me keep doing it over here because I have way more space to write over here. Sydney, I think you're confusing the process just slightly. So in terms of finding the top versus bottom, this is where you have the two choices. You can either do it algebraically, or you can do it graphically. Sydney, since your question is more on the algebraic way, I'm going to do that first. So in the algebraic way, once you've split it, intervals that you're working over based off of where the two functions intersect, you pick a test point, any test point you want. So I'm going to pick 1 and, well, any test point that's in that interval. So I need something between 0 and 2.382, so I chose 1. And then I need something between 2.382 and 4, so I chose 3. The two functions we're working with is y equals 0 and y equals x cubed minus 7x squared plus 11x. So I take that that x equals 1 and plug it into both functions. There's nowhere to plug an x into a y equals 0. It just always gives you 0. But then, can I name this f of x? When I plug that value of 1 into the x cubed function, I get 5. Now, Sydney, that 5 is literally just for this step, and then it never comes into play ever again. So essentially, the only thing we use this 5 for is to say, is 5 larger or less than 0? Like we're comparing these two numbers. Which one's larger? 5 is larger, which means that in the interval 0 to 2.382, the x cubed function is on top, and now we forget about the 5 ever existing. And similarly, when we do the other one, we plug in 3 to both functions. When I plug in 3 to the x cubed thing, I get -3. So when we get that, we're going to compare -3 and 0, which one is larger? 0 is, and now we forget about it. So we don't really do anything with these numbers at all. It's just to figure out which one has a larger y value. And once we find which one has a larger y value, once I've essentially boxed which function it came from, I forget it. Yes, kind of. Well, not the bounds. It's how to write the integrand. So the bounds are set by these intervals. Those intervals give us our bounds, but this thing tells us which function to put first in the integrand. So the integrands that we're calculating over, so we're going from 0 to 2.382. We need some top function minus some bottom function. So essentially the fact that 5 is larger than 0 means that the x cubed minus 7x squared plus 11x is the top function. So when I go to write my top versus bottom, top minus bottom, I know that my function was x cubed minus 7x squared plus 11x, and my bottom function was essentially y equals 0. So it's used to help us find which function comes first in the integrand. Now, really quickly over to the graphic step. If you want to graph it, you graph the doodads. So this was the 2.32 and this was the 4.6. 618. So we're essentially cutting it off right here. That's obnoxious. Cutting it off right here. So remember the functions we're comparing. We're comparing this cubic thing that we drew, and we're comparing the cubic thing to the x-axis. So essentially we're just saying which one is on top of the other in each section. Well, if you look at kind of this first section here, the 0 to 2.382, the cubic thing is on top. So that means that our top function is going to be the x cubed thing, which is exactly what we came out to with the algebraic way. But then once we hit 2.382, then the x-axis, the x-axis turns out to be on top of the function. So then in the second integral that I didn't write down, the second integral from 2.382 to 4, and that's why, you know, I boxed the one that was with y equals 0. That means the 0 function's on top, and the x cubed minus 7x squared plus 11x is on bottom. Yeah, David?
Okay, if you were to graph, what if you have something similar to the answer of 2.382? Like, okay, say if you have something similar to, or something close to it.
I don't know if I quite understand your question. Are you talking about the algebraic way? Like if we chose something really close to 2.382?
Yeah.
Okay. It shouldn't matter what number you choose. It should still turn out to be that one of them is larger or smaller than the other. So even say if I took, say in this interval, I let my value be 2.3, because that's technically less than 2.382. So I could plug that in. So if I plug that into my, you know, x cubed function, what the heck am I going to get? So 2.3 cubed minus 7 times 2.3 squared plus 11 times 2.3, I get 0.437, which is still larger than 0. So this would still be our top function. It shouldn't matter what number you pick, as long as it's in that interval.
Okay, that'll work.
Yeah, Savannah, exactly. I just need any point I want between 0 and 2.382, and then absolutely any point I want between 2.382 and 4. And I just decided to choose 1 and 3 because they made me happy. It's kind of like when we were doing those derivative number lines, and you kind of, you know, have your sections and you just picked a point between those numbers. Same kind of idea here. We have our intervals, we get to pick whatever number makes us happy. I think that was all the questions people asked. Anastasia, did that help clear things up? With top versus bottom?
Not really, but it's okay. I think I'm just confused on the concept.
We've got a couple more, so hopefully by the end of doing a couple more, maybe it'll stick. Okay. Any more questions on this one before we head over to do a couple more? Okay. Let me actually try to reshare it the usual way. And blank. There we go. Okay. We do have a slight break of those. We're going to come back to ones like those in a second, but just a small little break for a slightly different thing. So say for each of the following, we want to determine if the integral from 0 to 5 of that function that's graphed would be positive, negative, or approximately 0. Now, this goes back to the idea of area above the x-axis is counted positive, area below the x-axis is counted negative. So if we look at this first one, so we want to go from 0 to 5, so we kind of need to consider all the stuff that's there. So we have this little tiny bit that's above the x-axis at the very end. And then we have most of the stuff that's below the x-axis here. So since most of that stuff is below the x-axis, when we're calculating the generic integral from 0 to 5, this would turn out to be negative. I don't know what the number is because I don't know what the function is, but I know that it would turn out to be negative because most of this stuff is below the x-axis. So I want to be really clear. In a general integral, area below the x-axis is counted as negative. What we were just doing is specifically manipulating the integrals to force them to be positive. That's why we need to find which function is on top of the other to make sure that anything is forced into being positive, but in a generic integral, any area below the x-axis is negative. Now in the second one, we have some area here that's above the x-axis, and then some area here that's below the x-axis. Now note that it seems like there's more area above than below, right? So the area that's above does seem a bit bigger than the area that's below. So that means that even though that area below the x-axis is going to be counted as negative and is going to kind of subtract some of that area from the top, it's going to kind of take away some of it. There's more area on top, so this would result in a positive result. The result would end up being positive because there's more area above the x-axis. Whereas in this last one, if we find that there's kind of this area above the x-axis here, and then some, yeah, put it in a bad spot, and then some below the x-axis here, notice that those two areas look pretty much the same. Well, the same size, I should say. They look approximately the same size. So even though that one on the left is going to be treated positive and the one on the right is going to be treated negative, since they're about the same size, they're actually going to end up canceling each other out. So this one's going to end up being approximately 0. Sorry, maintenance people. So, no, Jack, the exam on Thursday is just on chapters 5 and 6. Well, the sections of chapter 5 and 6 that we've covered. It does not include the chapter 4 stuff. Okay, one other thing I want to say about these types of questions is, so here we didn't have a function, we didn't have any values for these areas, but there are certain types of questions where I could say we go back to this middle one, and I say, okay, well, this is the function, and the amount of stuff that's above the x-axis is 5, and the amount of stuff that's below the x-axis is 3. And then say I asked you to calculate the integral. So if I then asked you to calculate the integral, so I'll write it in red to keep track of that. It's a slightly different question. So if I wanted the integral from 0 to 5, since I know that there's a total amount of 5 above the x-axis, if you will, a total amount of stuff of 5, but then the area below the x-axis is 3, but since it's below the x-axis, it needs to be counted as negative, so we need to subtract it. So the integral would actually end up being 2. If I asked you in that same type of idea for the total area, that would be 5 plus 3, because then essentially that's the difference, is that if you're asked to find a general integral, you treat any area below the x-axis as negative. But in this new stuff that we've been doing in the long process that we just did for the last two, that's when it's a total area question, and we're essentially forcing anything below the x-axis to be treated as positive. So that's the kind of difference between the two. But you could also have questions like that where I kind of give you the amount of stuff in a piece and ask you for the integral. I believe there's some of those on your review. Anyway, questions about that before we go on to these last two area between function examples? Okay. So, these last two are slightly different than the ones we've already done, specifically because it's now giving us two different functions, and one of them is not the x-axis. It's the same exact process. It's just that one of them is no longer the x-axis. So say we want to find the area enclosed by the functions 4x minus x squared and 1/2 x to the 3/2. Now there's one thing for this one we're gonna have to use our calculator for. And that's to find where they intersect. Finding where these two intersect by hand, I honestly don't even know if I can do it. But the first thing we need to do, just like with the last ones, is find where they intersect. Oh, let me change back to regular color. Don't worry, for the ones that would come up on an exam, you'd be able to do them without your calculator. You know, they'd factor, or you could use the quadratic. Well, I should be careful with saying without your calculator. Without having to use the process we're about to do. You might have to use it to like plug in some numbers and see what it equals, but you won't have to do this exact process. You can if you want to, you just don't have to. But finding where those intersect by hand, I honestly don't even know how to do it. I might if I think about it, but I don't want to think about it. So what we're going to do, we're going to call upon our trusty dusty calculator. Actually, let me share my screen like this so that I can still get the stuff in there. All right, so if you want to do this by your calculator, what you're going to do is you're going to hit the y equals key. Oh, they're already in there. Okay, well then. And if you obviously won't already have them in there, you're going to want to put both of those functions into your calculator. So I'll wait a couple seconds in case anyone's trying to follow along exactly. Usually I'd be punching this in with you, but they're already in there. So you put each function one on each line. Once you have both of those in there, I like to just graph them, so I hit the graph key. You don't really need to see what they look like graphed. You can just jump to the next thing, but I just like to go to the graph screen real quick first. But then to find where they intersect, what you can do is you can hit second and the trace button, which is right next to the graph button. Remember, my little key press history is in the bottom here in case you missed something. Second, trace. And then you can either scroll down to number 5, intersect, or just hit number 5 on the number pad. Now, if the only two functions that you have are the two functions that you need, which usually is best practice, just delete everything else and just put the two things that you need in there, you're going to hit enter, enter, until it says guess. And then, so of course, mine's already there again. I think yours will probably start back here at the origin. What you're going to do is you're going to press the, over keys until you bring your little blinky flower dude over to approximately where they intersect. It doesn't have to be perfect. It just has to be in like the very general vicinity. You want to get as close as possible and then enter again. And it'll tell you where they intersect. Hooray! So these two intersect at x equals 3. I'm going to say 3.12. I'm going to round to 3 decimal places. So 3.12 is where those two intersected. Again, you won't have to do that process on your exam. It'll be able to be done via algebra. But if you like that technique, you can use it. But all right. And let me just write use calculator in case someone's looking at this later and wonders where the heck I got that from. So now we're given the kind of half an interval, if you will, of x is greater than or equal to 0. So we're not really told where to stop. So if you're not told where to stop, or maybe you're not given an interval at all, if you're not told, what numbers to look between, you're going to use the numbers you get from when you found where they intersect. So here we're essentially told to start at 0. And since we're not told when to stop, we're going to stop at the intersection point. And now I've kind of set myself up to do the algebraic way. So if I'm doing the algebraic way, I would pick a number. Why do you keep doing that? I'm going to pick a number between 0 and 3.12. So I'm going to pick 1 because that makes me happy. And I'm going to plug 1 into both functions. Now here it's a bit more complicated because one of them doesn't automatically give us 0, so we have to be a bit more careful here. So we'll get 3 compared to 1/2. Again, it shouldn't matter which number you pick in that interval. If you picked 2, you would still get that f of x is larger than g of x. So we're oh my goodness. We're finding that g of x is on top here because it has the larger y value. So remember, the point of doing that the algebraic way is to find out which one has a larger y value. And the reason it doesn't matter what point we pick is because it's not going to change unless they intersect. So during that entire interval, since they don't intersect in that interval, they intersect at the end of it, there's no way for it to switch one of them to be on top of the other. So that's why we find where they intersect, because we have to split it up in case it does change. But once we've split it up or created the intervals, it's not going to change in the middle of that interval, so we can just pick whatever number we want. Or you could, of course, do this graphically, and I mean, we kind of already had the graphs in our calculator, so that might have been a nice idea. So let me remind myself what this looks like. So we have this and this. So the essentially that quadratic piece is on top, and the quadratic is the 4x minus x squared piece. Once you find which is on top of the other, you're ready to do your integral from 0 to 3.12. Top function was the 4x minus x squared minus your bottom function of 1/2 x to the 3/2. Again, in terms of these questions, this is at this point you could punch that into your calculator. So if you punch it into your calculator, you will get an answer of well, if you do it separately, you would get 1/3 in the first one. No, what am I doing? Sorry. I'll come back to that in a second. You should get 16.6 repeating, or like 16.667 if you prefer to cut it off. No, I'm sorry. I'm looking at the wrong question on my notes. I'm so sorry. You should get 5.06. Sorry. If you're doing this by hand, your antiderivative would be the following. Oh Lord, it's going to be x to the 5/2, 1/2 times 2/5. So from 0 to 3.12. And again, if you plug in your top bound minus your bottom bound, you would still get 5.906. Concerns? Okay. We'll wait a couple more seconds in case someone's still writing something down. We've got one more, and then it'll be kind of a free-for-all question time. All right. So for this last one, same process. Find where they intersect, find the intervals, top minus bottom, call it a day. So we want to find where these two functions intersect. So we have square root of x equals x squared. Now this one we can do algebraically, so let's go ahead and do that. So if we want to get rid of the square root on the left, we're going to have to square both sides. So we'll get x equals x to the fourth. Now, a lot of people will usually try to divide by x at this point. And while technically correct if you think about it enough, it's going to lead to a lot of people making a mistake. So I always suggest never dividing by, well, maybe not never, avoiding at all costs dividing by a variable. So what you should do instead, and I'll show you why it's a problem in a second, but let me just finish this out first. So what you should do instead is collect all of the variables onto the same side of the equation. So instead of dividing by x, let's subtract it over the other side. Because then what happens is we can pull x out of both terms. Then we can set each piece equal to 0. So we get x equals 0 and x equals 1. So let's say that, I'm going to erase this in a second, but let's say that you had thought to divide both sides by x. That's what you thought to do to solve that algebraically. You would get here. And you would get that x equals 1, which is an answer. But what about the x equals 0 answer? You didn't get that one. The reason that happens is divide by something, that thing can't be 0. Because you can't divide by 0 because that makes them explode and me cry at night, so you shouldn't do it. So when you divide by x, you essentially need to assume that it's not 0. So essentially when you divide by that x, you're essentially getting rid of that possible solution. And unless you then consider that solution separately, you're wrong. So that's why you should avoid at all costs dividing by variables. So just in case. Don't divide by variables. Collect them all over to the same side. And yep. So just like when you have like x squared equals 1, you have to square root both sides. Here we would take the cube root. So x cubed being equal to 1, to essentially get rid of that x cubed, we would have to cube root both sides. So the cube root and the cubed cancel each other out. And then unlike with x squared, since this is an odd power, we don't need a plus minus. And the cube root of 1 is 1. So that's why. So yeah, just in case, odd powers, you don't need a plus minus. When you take a square root, a fourth root, a sixth root, you need the plus minus. But with odd roots, you don't. So we've essentially found where they intersect. So we kind of care about 0, but it's an endpoint, so we also kind of don't care about it. The main one we care about is 1, so we need to split this up from 0 to 1 and from 1 to 4. I'm going to do the graphic way first. I'm going to do both of them, but let me do the graphic way first this time around. So square root of x looks like this. No, x squared. What is wrong with me? X squared looks like that. And then the square root of x looks like this. And then they essentially intersect at 1. So this would be where 1 is. So if we're going from 1 all the way up to 4, I know this isn't to scale, but let's say that 4 is right there. So it's not to scale, but it doesn't really have to be to scale. So between 0 and 1, this function's on top of the other. It's higher up than the other one. Whereas in the second piece from 1 to 4, now the quadratic is on top. So we're essentially saying that in 0 to 1, square root of x seems to be on top. And in the 1 to 4 piece, x squared seems to be on top. Let me just verify that algebraically. Again, you don't have to do both, but just for so a number between 1 and 4, I'm going to pick 2. So if we plug these into both functions, to just triple check that we got the right top function. So the square root of 0.5 is about 0.707. And 1/2 squared is 0.25. So which one of those numbers is larger? 0.707. So the square root of x is on top, which we already knew. And then if I plug 2 into both functions, the square root of is approximately 1.414. And then 2 squared is 4. So 4 is larger than 1.414. So x squared is on top, which again, we already knew. So once you have once you have all of the intervals and you have which one is on top of the other in each of those intervals, I can't talk today. And if the thing will stop zooming out randomly, then we're ready to set up our integrals. I'm gonna run out of space again. I need to add more space for these apparently. Let me do this. Whoosh, whoosh, whoosh. There we go. So our first integral is from 0 to 1. The top function was the square root of x. So we have the square root of x minus x squared, squared. And then we have an integral from 1 to 4, but then the top function was x squared. Again, at this point, you can plug them into your calculator if your calculator can do so. You would get 1/3 for the first integral. And I hate writing mixed numbers, but I'm going to write it as a mixed number. Essentially 16.3 repeating for the second one. So you'll get 16.6 repeating or 16.667 or whatever, however you'd like to chop it off. If you want to know the antiderivatives, they would be, I'm going to not put the plus c for the sake of space, because again, when you're doing these, the c's always cancel each other out when you end up with the bounds. So yeah, see, I would have run out of space. And of course, to finish it out that way, you would have to do the top bound minus bottom bound calculation. Questions, concerns? It's a good question. And so someone else asked me this the other day too. Let me go back to where the heck? There we go. So her question, in case people don't have chat open, is how do we know when to add or when to subtract to find the area? Oh, actually, your question might have different pieces to it. I think maybe part of what you're asking is, so like in the last one, we had integrals that were added together, but then we had functions that were subtracted. When you're finding area between two functions, it's always an integral of a top function minus a bottom function. So when you're finding area, the integrands should always have them. But if you have multiple intervals, those intervals and the integrals that result from them should always be added together. Is that your question, or is your question more about kind of, where is it? Where am I? Is your question more, oh crap. You can't see what I'm doing. Is your question more about this doodad that I'd been talking about earlier? Kira. Okay. So do we have to do them by hand on the exam? Okay, so in terms of the exam, for these area questions, for the area questions, all you have to do, well, I shouldn't say it like that. There's still lots of work to show. For the area questions, the work I need is essentially all of the work to get to the integral. So you need to show me, all this work over here of finding where they intersect and finding which one's on top and which one's on the bottom. You don't have to do both ways. Well, sorry, you can either find it algebraically or graphically. You have to find which one's on top and which one's on bottom, and you get to choose graphically or algebraically. And so you have to show me all of the work to getting up to writing the integral, and then you can plug it into your calculator. But there will be questions on your exam where it's just like calculate the integral of 0 to 1 of 6e to the 2x dx, which will not be part of an area question. I'll just ask you this. Those ones you'll do by hand. So you do still need to know how to do the integrals by hand, but when it comes to an area question, you do the work up to the integral and then you can plug it into your calculator. And yes, I try to be very specific with my instructions to make sure that there's no confusion. How many questions on the exam approximately? So right now, the only one I have fully written is the 50-minute one, which is not for you guys, it's for my other two classes. And theirs turned out to be 11 questions. Well, if you count the parts, so if you count the parts of the questions, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, so 13 parts. Yours usually have 1 or 2 more questions than theirs do, so probably around 13, maybe 15 pieces. So yeah, like a generic one done by hand, Anastasia, like one of the ones that you'd actually have to do by hand, I can do one of those. So today, the one that's boxed on the screen right now, Sydney? Is that the one you're talking about? Okay, so yeah, let me just do this one then. So if you were just given this question, calculate the integral from 0 to 1 of 6e to the 2x. This has nothing to do with intersect, top, bottom, anything like that. When you just have an integral, this is your antiderivative, plug in your bounds. So we need our antiderivative first. So the 6 comes along for the ride. And then we're into the e to the kx situation. So we keep the e to the kx and then divide by that k value plus c from 0 to 1. So of course we could clean up those constants a little bit. And then here is where, and this is what I haven't been writing down on the area questions because I'm lazy, to be quite honest. If anyone wanted to see it, you could ask me and I'll do it. But here's when we take our top bound. So our top bound is 1, so we plug in 1 everywhere we see an x. And then we plug in 0 everywhere we see an x, and we subtract off that value because remember the quadratic formula. The fundamental theorem of calculus is the thing that says f of b minus f of a, and that's where we get our top bound minus bottom bound thing from. So the answer to this would be e3 to this 3e squared minus 3e to the 0th, which would also semi-reduce to this. But so when it just says calculate, here's an integral, there's none of the hoopla that we were kind of just doing. It's the find the antiderivative, plug in the bounds. So office hours, I have some tomorrow after starting at 2:30. I do have one person who wanted to stop by for a different class, but his question shouldn't take too long. But from 2:30 to 4 tomorrow is when my office hours are. Oh, and I also have some before your exam on Thursday. I have office hours between 11:30 and 12:30 on Thursday. Whew. So, okay, Sean, clarification. I'm sorry. No, No, I did it bad. So the k value is technically 2. But the antiderivative of e to the kx gets 1 over k. So that's why it turned into a 1/2. The k value is technically 2. The antiderivative rule for e to the kx, we have to essentially divide by that. So it's 1 over 2 instead of 2. Does that make sense? Okay, we've got 15 minutes. It's essentially open question time. So, anything you want to see? I can try to do an example. Oh, another thing, what I'm going to do, since you guys didn't have any 5-3 homework, because that would have been horrendous of me to do to you, I'm going to put up some optional 5-3 problems in Wiley in case you want to have some extra practice for this 5-3 stuff. So I'll put some questions up on Wiley, purely optional. Can you work out an antiderivative problem? Sure, with a square root. Can do. Do you want bounds? Not bounds? I'll do bounds. Let's just keep doing bounds. Okay. My brain's starting to get a little fried though, so let's do 1 to 4 of, let's do 2 times the square root of x. You know what? Plus 1. Sure. So, first thing we'd want to do is rewrite this as x to the 1/2. Also, if you don't have questions, you can feel free to leave if you want, because we're done the new content for the day. And now that we have it rewritten as x to the 1/2, we can use the anti-power rule. So that 2 in the front comes along for the ride. Okay, so if it's just a regular square root, yes. If it's a cube root, that's a 1/3. If it's, any other number out there, it's 1 over that number. If it's got a power on the inside, the power becomes the numerator of the fraction. So if it's a regular old square root, then yes, it'll always be a 1/2. But if it's anything besides a regular old square root just by itself, then things get wonky. So, brain. We add the power, so 1/2 plus 1 would be 3/2, and we divide by that new power. And then the antiderivative of 1 is x plus c from 1 to 4. Dividing by a fraction is the same as multiplying by its reciprocal. So this would reduce to 4/3 x to the 3/2 plus x plus c from 1 to 4. I didn't choose my coefficient wisely. So we're going to plug in our top bound. Subtract what we get when we plug in our bottom bound. So 4 to the 3/2 should actually end up being a semi-nice number. 8. So 4/3 times 8 plus 4 minus 4/3 minus 1. Okay, so that front term is a little gross. So this becomes 12.3 repeating, otherwise known as 37/3. So whenever you have a root, first thing you want to do is change it into a fractional exponent. The number on the root becomes the denominator of the fraction, and if there's any power inside of the root, it becomes the numerator. Now remember, on a regular old square root. It's kind of got a baby 2 in the front, but we just don't write it. But if that number is anything besides a 2, then the denominator of the fractional exponent will be that number. Cool. Any other requests? Also, there was a typo in the a hand typo in the goodness, my brain. The exam review answers. So if you had like downloaded it like before an hour ago, you'll want to re-download it because I messed something up. But it's corrected. It's up now. So if you open it up at this point, it's fine. If you think you see any other mistakes, just let me know. Got a little less than 10 minutes. If there are any other requests for problems. Otherwise, feel free to leave.